This is Geometry Lesson 3.5, Justifying Conclusions. The big idea says the basis of mathematical reasoning is the making of conclusions justified by definitions, postulates, or theorems. So we've taken some time and looked at what makes a good definition, and we've studied some different postulates and theorems. And so we're going to start using those now to prove or justify some conclusions for conditional statements. So the definition of a proof, we're going to talk about proofs a lot. A proof of a conditional is a sequence of justified conclusions, starting with the antecedent and ending with the consequent. So there's lots of words there that we've used before. Let's make sure we remember what they all mean. Conditional is a if P, then Q statement. And a proof of a conditional is a sequence, which just means in a row, 1, 2, 3, 4, 5, of justified conclusions. Why are we allowed to conclude this? Starting with P, the antecedent, and ending with Q, the consequent. All right, so this is what a basic proof looks like. You have a given, and we're trying to prove something. The given is like your P, and what you're trying to prove is like your Q. So you could read this: if 4x minus 12 equals 10, then x equals 5.5. That's what we would get if we solved this algebraically. And we're going to write a proof and show our justifications. All right, and that's basically what a proof is explaining why we're allowed to do what we do and conclude that sure enough, x equals 5.5. So this is done for you here. Here's your conclusions. We started out with our given. That's always going to be the first line of a proof, is whatever was given to you. So you automatically just write that on the first spot, and your justification is just that it was given. And then the last line of your proof, they're going to be a different amount of lines every time, but the last line of your proof is going to be whatever you're trying to prove, which you could consider your Q statement or your consequent. Okay, and then we have to get there along the way, and not just get there by showing our steps, but also show our justifications. And we started doing this a little bit in 3.4. All right, so 4x minus 12 equals 10 was given to us. To get from there to there, the minus 12 has disappeared and 10 has become 22. So we know we added 12 to both sides to get to this point. All right, and the justification for that is the addition property of equality. You're allowed to add the same number to both sides of an equation, and it maintains its equality. So that's the addition property of equality that gets us to here. And then we notice from this step to step 3, we've lost the 4 on this side, and 22 became 5.5. And we know from all of our studies in algebra that we would be dividing there. But we talked about in the previous sections that we are going to look at the addition property and multiplication property to cover everything that we need here. So even though this looks like division, that's the same as multiplying by 1/4. Dividing by 4 or multiplying by 1/4 is the same thing. And so our justification for this step is the multiplication property, not the division property. The multiplication property of equality. We've multiplied both sides by 1/4. So that's a basic looking proof. And this looks similar to some things that we already touched on in 3.4. So we want to start to see there's a given and there's something you're trying to prove. It's an if-then statement. If P, then Q. If 4x minus 12 equals 10, then x equals 5.5. You're going to have two columns, your conclusions, which are basically your steps to get from the given to whatever you're trying to prove, and then your justifications on the right. Now this is an algebra proof, really. Okay, even if we were solving a geometry problem, this is algebra that we're doing here. Let's take a look at one that is a little more specific to geometry. So example number 2, P and Q are points on a circle with center O. So we know that P and Q are actually on the outside of the circle when it says on the circle. And we know that O is in the center. It's not just a random point in the middle or in the interior of this circle. We want to prove that OP, that segment, is equal to OQ. So again, when you write a proof, the first line is always going to be your given. So your conclusion is P and Q are points on a circle with center O. That was given to us. So the justification there is given. This is a quick, easy, short proof. As you can see, we know that OP equals OQ because of the definition of a circle. Now, if you were writing this proof yourself, you could just stop right there. But because this is your notes, we want to make sure we understand why we can put this. So it says a circle is a set of points in a plane at a given distance from a given point. So the definition of a circle tells us that every point that's on the outside of that circle is the same distance, a given distance from the center. So no matter where I go on this circle, we know the radius is the same. Each one of these would be radii. Okay, so just by the definition of a circle, I can prove that these two lines are equal to each other. So that's a nice, short, sweet proof. Let's flip it over. Example number 3. Let's get this a little more focused for you. So the given is the figure at the right. And we can conclude some stuff from that. If you notice that the first line, since the given was just a picture, on your first line, you're not going to draw a picture. You're going to write something that you can conclude from the picture. We're trying to prove that the measure of angle 1 plus the measure of angle 2 equals 180. Now, we already know that. We've talked about the theorems that prove that, but we're going to actually spell it out here in this proof. So the first thing that we are allowed to conclude is that 1 and 2 form a linear pair that was given from the picture. Okay, the picture shows two angles forming a straight line. Therefore, we know angle 1 and angle 2 form a linear pair. Okay, from that, we can conclude that 1 and 2 are supplementary angles. How do we know that? How do we know that? So this would be your linear pair theorem. 1 and 2 are supplementary angles. The linear pair theorem says any two angles that form a line that are a linear pair are supplementary. Okay, so the picture gives us two angles forming a line. The linear pair theorem tells us that those two angles have to be supplementary. So therefore, angles 1 and 2 have to add up to 180. And that's by the definition of not linear pairs. So this kind of gets a little ticky-tacky. That's kind of what proofs are. So the linear pair theorem tells us that the angles are supplementary. Okay, the supplementary definition tells us that the angles add up to 180. So this is the definition of supplementary angles. So you kind of have to go step by step by step. We can't just jump from one to the next. So we started off by seeing a picture. Two angles form a linear pair in that picture. We know that those angles are supplementary because of the linear pair theorem, which we've studied. And therefore, angles 1 and 2 add up to 180 because of the definition of supplementary angles. All right, let's try one where we have to fill in the entire thing ourselves. So here in this additional example, the given is angles 1 and 2 add up to 90. Remember, you can't ever assume that unless it's given to you in the picture. Even if it just said, similar to this, the figure below, as the given, but in the picture it showed the 90-degree angle, then that would be given to you. Okay, if there's markings in the picture that show you there's a 90 or that things are equal, okay, that's part of your given, even if it's not written out. They also tell you that angles 2 and 3 add up to 90 degrees. So we're going to try and prove that the measure of angle 1 is equal to the measure of angle 3. Now, some people might look at this and say, well, of course, they're vertical angles. They're not actually vertical angles, though. So if you look at this side of 1 and you extend it through this line, it does become a side of angle 3. But for things to be vertical, that has to be true of both sides. And this side of angle 3, if I extend it, is not the other side of angle 1. Although they look similar, they are not the extension of each other. So these are not vertical angles. You cannot assume that they are equal based on the vertical angles theorem. So we're going to use some different theorems to get through this one. So we're going to make one of these proofs. We're going to have our conclusions and our justifications. Now remember, we always start with our given. So our given, you're going to write the whole thing out. The measure of angle 1 plus the measure of angle 2 equals 90, as well as the measure of angle 2 plus the measure of angle 3 equals 90. And you number your conclusions and your justifications so that they line up. So our justification here is that they're given. So how can we prove that these angles 1 and 3 are equal? So the clue is kind of what's given to you. Angle 1 and 2 are adding up to 90. And notice they didn't give you like a 4 in here and say 4 and 3 add up to 90. That's not what they said. They said angle 2 and 3 also add up to 90. So 1 plus 2 is 90 and 3 plus 2 is 90. So both of these are being added to 2 and they're adding up to 90. Okay, so we want to start using some of those properties that deal with maybe two things being equal to the same thing or two things being added together to equal the same thing. All right, so our second line, what we want to conclude is, if you take a look at this first line, this statement equals 90 and this statement equals 90. They both equal 90, which means they both equal each other. Okay, that's the transitive property. You also could say, since 90 equals this, I can substitute this in for 90. So you actually have two different justifications that we could use here, but both of them are going to say that this equals this because both of them are equaling 90. So I know the measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3. And again, the reason I know that is because this equals 90 and this equals 90, which means they equal each other. So this could be your transitive property. Which, if you remember, says if A equals B and B equals C, then, so two things equaling the same, A equals B, C equals B, then we know that A equals C. Now again, you don't have to write that out. You can just say transitive property, but I'm reminding you of it. You also could call this the substitution property. Okay, if we know that this equals 90, I can take this and plug it in for 90 over here. So we're used to seeing that with an x, like x equals 5. So I can plug in 5 for x over here. That's substitution. This is also substitution. Okay, if I know this equals 90, I can replace the 90 with this, and they end up equal each other. So there's two options here, the transitive property or the substitution, but we're going to go with transitive there. Okay, and now we have to get from here to what we want to prove. So we want the measure of angle 1 to equal the measure of angle 3. If you take a look, we've got this plus measure of angle 2 on both sides. Just think about these as variables right now, not even what they represent. If I just wanted to get rid of this, or if I somehow got rid of it, okay, I would have what I'm trying to prove. The measure of angle 1 equals the measure of angle 3. And we know that we're allowed to add or subtract things to both sides of the equation, and it maintains its equality, which means it's still true. So I can minus the measure of angle 2, think about it just as a variable, from both sides, and it's going to go away. Now, you don't have to show this step, but I want you to look back at your notes and understand what we did. So this gets canceled on both sides, and what are we left with? The measure of angle 1 equals the measure of angle 3. And how did we get there? This is the addition property. And remember, there's two addition properties. There's inequalities and equalities. So you want to state which one it is. We're dealing with an equal sign here. So this is the addition property of equality. So if this, then this, how did we get there? Just a quick review again. We knew two different things both equaled 90. So that means they equaled each other by the transitive property. we saw that we had the measure of angle 2 on both sides, so it could be canceled by minusing it or adding a negative. Okay, so those go away. We're left with the measure of angle 1 has to equal the measure of angle 3 based on the addition property of equality.